Hello, I was a bit bored, so I decided to record a tutorial about haskell and I'll write a Brainfuck interpreter. So if you don't know Brainfuck, this is a really nice language which is designed around a few commands such as the greater than, the less than sign, the plus, the minus. Mainly you have a big memory and you have an offset on this memory. So I will do a little draw, draw.txt. Okay, you have a memory with 0, 0, 0, 0, 0, 0, 0, and you have an offset on this memory. For example, the offset is here. Okay, and with the greater than, you can move the offset one side on the right. With the less than, you can move the offset one side on the left direction. With the plus sign, you can increase the memory, which is at the current offset. With the minus sign, you can decrease the memory, which is at the current offset. With the point side, you can output the byte as the data at the current memory offset. So it means that it will output the car 0 here. And if you have something like a 65, it will output the car 65. And with a comma, you can ask for a car and it will be stored at your current memory offset. And there is also loops based on both squared brackets. The opening square bracket is a test, so it tests that the current memory offset is different from 0. If it's different from 0, it will execute as many instructions as stored until the next closing bracket. And the closing bracket is just the loop jump, so it basically jumps to the beginning and do the test again. So we'll do this interpreter in Haskell just to have fun. So I will start to create an Haskell project using stack. So stack new Brainfuck. Okay, it will create a Brainfuck directory, download a building plan using a GST7 7.10. I'd prefer GST8, but the default building plan is GST7. So, by the way, we don't care about that. So, okay, I have a directory called Brainfuck, and inside this directory there is many things. We don't care about most of them. The point is that we can launch an Haskell shell, which will build my project, and then we have an Haskell shell. Okay, I will just for now add one dependency in the brainfuck.cabal, which is the list of this file contains the detail of the project and the list of dependencies. And I will add a dependency on my library. Mostly the dependency is megaparsec, which is a parsing library. Okay. Okay. Stack build. It will download and build the megaparsec dependency, so we'll be able to parse the Brainfuck language. So during that time, I will start my program is inside the src/lib directory. In src, I will move this and I will call it brainfuck.hs. Okay, and rename the module Brainfuck. Perhaps it's too small, so I will increase a bit the size of the text, and I will decide to export everything. In Haskell, you can limit the list of exported symbol from a module, putting the name of the symbol just between the model name and the where clause. And my module contains no function. I decided to do that. Okay, and yes, it's a bit of boilerplate because at the beginning yeah, the default project makes some assumption. It creates a lib file which contains a function, stupid function. So, okay, now we'll start. What is Brainfuck? Brainfuck, it's only this list of instructions. So I will just copy paste them in my file to have a reference. Okay, now I will create data type which is able to represent all the possible instruction. So this data type, I will call it a command, a CMD. It's or an instruction. Instruction. Okay, and an instruction can be forward, which increase the data point, the memory of it. We call it forward. Okay, okay, or backward, or increment, or decrement, or output, or input. And for the special case which will store the loop, we'll call it loop, and the loop contains a list of instructions and will derive show. Okay, what does that mean? It means that there is we create a type which is called instruction with different constructor. A constructor is one representation of a type, and this type instruction can contain you can choose between different constructors which are forward, backward, increment, decrement, output, input, and loop. All of those constructors, but the last one, are just an array constructor. They do not have any argument. The last one, loop, is a constructor with one argument, which is a list of instructions. So if we load the interactive shell, I must set up my project file because the export module is not live, it's Brainfuck now. Okay. Okay, it's building. Yeah, happy building. Okay, we have forward, backward, okay. And we have a loop which contains a list of different instructions. Okay, we are pretty happy with that. Now we can suppose that a program is a list of instructions. So we want to evaluate the program, and to do that we'll need the memory. And as I said, the memory in Brainfuck is an infinite band of memory with an offset somewhere. So, and this memory contains infinitely a few zeros. So the idea is that we will represent this memory. The caret is represent the offset inside the memory. We will represent this memory with two lists. One list, the right list, and one list, the left list, which is stored in reverse order. Okay, so for example, there is already some data in this list. Okay, and going to the right, I mean the forward instruction, will just move. We just move the one item from the right list to the left list. So we'll get this, and now the caret is virtually on the 2. Okay, and going to the left will give us going backward will give us the opposite direction. Okay, and we need a data type able to represent this stuff. I'm using list here because the action of going forward or backward will be in constant time using a list head. So it's convenient. But also, yeah, it's it's kind of an interesting solution. Also, it will handle easily infinite. By the way, infinite as such, as long as the memory handles it, infinite list, because we can easily add numbers on the different side of the list when they're empty. So to do this, we will create a band. This is the memory, or memory, we call it memory. And a memory is a left list of int and a right list of int. This is it. Deriving show to be able to display it. Okay, so now what's an empty memory? Empty memory. It's a memory with empty list, obviously. Okay. We'll write types, else haskell will the compiler will complain the bytes. Okay. Now we want to go to the left or the right of the memory. So go forward, takes a memory and return a modified memory. Go forward, memory, okay. And when we want to go forward, we want to pick one item from the left list and put it, one item from the right list and put it on the left list. So there is the left list and there is the right list, which must contain one item. And we return a new list. Okay. But actually, haskell complains because I made a typo. Okay. Now it complains because I do not have handled one case. What happens if the right list is empty? That's interesting. If the right list is empty, it means that we'll just move and put a 0 on the left list. Empty means there is nothing yet, and nothing yet means the memory is default initial by 0. So we can do it like that. Go left, it's the symmetric operation. Memory, okay. Go left, we have a memory with a left side. Recall that the left side is store reversed, and the right side, and we just want to move one item from the left to the right. And again, there is the same issue when the list is empty. So if the list is empty, we'll just move a 0 to the other side. Okay. Now we want to get a value from the memory at the current offset. So read memory, a memory, and it returns an int. Read memory. We have decided by default that the value at the current offset is the first value of the right part of the memory. So we ignore the left part and we use the right part. The first value is x. And again, it complains because we do not handle the case where the memory is empty, and it will be handled easily by saying that in the case where the memory is empty, we'll put a 0. Okay, and we also write modify memory. Modify memory takes the memory, and I want a function which something which takes the memory and a modifying function. So it will take an int and returns an int on my memory. So modify memory, f, the modifying function, a memory with a left side we don't care about and a right side we care about, and we'll modify the first element of the memory. Memory left. We care about the left side, actually, we want to keep it. Memory f, the xs. Okay, and actually it complains just because yeah, actual no. Oh, it's modify memory. Sorry, it does not return an int, it returns a memory. Okay, and this is the same as usual. We do not handle a case where the memory is empty. So in the case of an empty memory, we'll just modify the zero value, just because by default we have 0. So modifying the 0 value fails an interesting default way. So we'll test all those functions in the iterative shell on the left side of my screen. Empty memory actually creates a memory. If we want to read memory of an empty memory, we'll get 0. Oh, that's right. If we want to modify memory and add 10, we'll get 10 if we read this memory offset, which is nice. Okay, now we'll modify by doing, we'll write an ink memory, which is modify memory +1. Okay, and excuse me, and we'll have a small test which is ink empty memory go left. Okay, go left, ink. Okay, go right, go right, go right, go right. Okay, I will write it differently because it's a bit painful to do this. I will write it using function composition. Okay, this will remove a few useless parentheses. And oh, there is no go right, excuse me. There is go forward, and go backward. Okay, and we'll ink 3 times the last position. What do we got? I suppose starting from an empty memory, we'll increment 2 times the starting offset. We go backward 1 time. We'll increment 1 time the current offset. We go forward 2 times. We increment 3 times the forward offset, which must be the second offset, and we'll go backward 1 time. So I guess we will get something in the memory which is located on an offset where there is a 2, and the next offset will have the previous will have a 1, and the next will have a 3, and go forward, go. Oh, I'm stupid. I call it go left. It's left backward. Okay, and obviously I should create again my ink. Okay, type A memory, ink, modify memory, ink, go backward. Oh, I did some mistake and I don't. Okay, this is a function from memory to memory, which obviously is what I want. Yes, it's a problem of operator priority. Okay, and actually I have what I said. My current offset is 2, the next one is 3, and the previous one is 1, which is what I wanted. So my memory is functioning correctly. So now I can write a Brainfuck interpreter, which will take, we'll call it run. It will take a list of instruction, and returns, actually, we don't care, it will return, I put IO because it will need to print car on the console or read car from the console, and I will return the memory. Okay, just for the sake of testing, we'll be able to see the final memory. So run, we call it inst, and we'll simply use a recursion which takes a default memory, empty memory, and our list of instruction. And we call our recursion go, and go will use a memory and a list of instruction. Okay, when the list is empty, we'll return the memory. Else we'll handle the first instruction, call it xxs, and we'll case match on the different case of instruction. Case x is x of. Okay, here we need to handle all the different cases: forward, backward, increment, decrement, output, input, and loop. And now that we wrote all this nice utility function memory, all the cases will be pretty easy to handle. So the forward case is handled by going forward on the memory. So we'll just recurse on. We just recurse and pass the new memory modified by going forward, and xs, which are the next instruction, because we are consuming the instruction one by one, and once an instruction is evaluated, it's done. Okay, backward. This is the same actually, but we need to go backward. Okay, we have increment. Increment, we just modify the memory in place. Modify memory +1. Okay. Decrement, we modify the memory -1. Okay. And it's not happy because there is a crappy subtract. There is a crappy parsing problem in Haskell, which is the -1 can be written -1 as a function. Here +1 is really a function. It will apply this function inside the memory. Okay. We do not handle output, input, and loop. So we'll try with, we start with input. Input. We'll get a char, get char, and we'll store this char inside the memory. To do that, I need a function from data.char, ord and char, and I'd always, my brain is broken about my brain is always broken about what are doing ord and char. Ord is ord. Okay, what is the type of ord? Ord take a char and return an int, which is exactly what we need. Get char returns a char. So we can store this inside the memory. So the recursion modify memory const ord c xs. Okay, there is many things happening here. So we'll try to explain them. I'll try to explain them. First, modify memory. Yes, I should pass memory. Okay, get char. The type of get char is IO char, which means it's an IO operation which return a char, and I need to use the invert arrow to get the char out of the IO operation. So I have a char. Now I want to modify the memory by storing the char, And the point is, I don't have a function write inside the memory a value. I have a function modify. So how can I use this function modify to set a value? I can use the const function. The const function is a really nice function which takes a first argument, another argument, and return the first. So here we partially apply it with the value we want to put in the memory, and it will take the other value which is already in the memory, totally ignore it, and store the first one. And we do the recursion. Okay, output. The output is a bit different because we just want to put a car. What is currently in the memory, read memory, and actually it doesn't work because it's returned an int, and we need a function from int to car, which is the function chr into car. Yes, I'm right. Okay, and go to the next step without modifying the memory. Actually, yeah. But okay, so now we handle all the cases except the loop. But first we'll try this, see how it works, to be sure that we do not we are right for now, and then we'll implement the loop. So we'll run a list of instructions, for example, increment, and this should give us a memory with 3 in the current case, which is right. Okay, now we'll do increment, forward, increment, backward, increment, and we'll get a memory with 2, 3, 1. Yes, that works. Decrement, we'll get 0. Okay. About input, run input. It's wait for car, a memory up. We'll have 97 inside it, so actually it works. Okay, the input works, and we'll input something, increment it, output something, and we'll get a, and I type A on my keyboard, and we'll get B, which was outputted. So everything works in this condition. So now, what about the loop? The loop contains a list of subcommands, and the idea is simple actually. We'll want to execute these subcommands and then continue our life. So go with the current memory. So we'll execute the subcommands. Let's memory prime. Memory prime is the result of executing the subcommands. And actually, we want to execute the subcommand only if the current offset is different from 0. So if read memory different from 0, then do this. If it's different from 0, we'll execute I may have done a parsing error somewhere. It's undefined, just for now. Why? Oh, okay. Yeah. If it's different from 0, we can execute the sub the sub loop, and then we'll simply recurse and call back the same instruction, which was, instead of recursing on xs like all the previous instruction, which means that we ignore the x instruction we are currently handling, we recurse to come back in the same loop subcase. It's the way of doing the loop. And if the memory is equal 0, we just continue to the next instruction. Please recall that the loop is one instruction which contains all the other instructions, and if we jump, we can jump to the next instruction. So, for example, we can start by a program. We'll do a program which contains we'll do a program which will simply increment and print for the whole life the current offset. So loop, and we'll loop, and our function we'll start by incrementing, because else the loop will never start. And we'll loop, and our loop will output and increment. Okay. And we'll get many crappy cars on the display, which means that it may work. Okay, we'll start with another. Oh, I killed my interpreter. We'll start with something smarter. We'll start by input to get the starting offset, and then a loop which output and decrement. And we'll start with the Z. And as we can see, it outputs every character and decrement until it reaches, I guess it reaches 0. So, by the way, and it ends with a memory with 0 inside it. By the way, our interpreter is now complete, and we can test it with the really classic hello world. These strings mean hello world. It's supposed to display hello world. So to do that, but the problem is that we do not know how to convert this string to a list of instructions. So now it's time to write a parser, and to do that, I will import the parser library, parsing library, megaparsec, which is a really nice parsing tool. So in a few lines we'll be able to parse everything. So I will import it qualified as P. Okay, so we want a parser about to parse an instruction. We'll write the parser close to the instruction, because yes, here I prefer. It will be easier for me to see the list of instructions. Okay. Parsing. Okay. Why doesn't... Perhaps the name is not megaparsec, it's text.megaparsec. So this is why it complains. Yes. It complains just about the fact that I'm not using yet the parser. So we write something which parsed an instruction, which is we'll get the parser for string too, because it will be easier for me. .p. Parser of instruction. Okay. Okay, a parser is something really nice, because you can create it using different combinators and return a different type from what you parsed. For example, there is the parse test function, import text.mega parsec parse test, which takes a parser, which is created by combining many functions, and a string. So for example, we'll try to parse the parser char a using the string ABC, and obviously it is able to parse the char a. It returns what he parsed. If we wrote BC, we'll get nothing. Okay, but a parser can also return something different. For example, if you want a parser which parse instruction, we can parse the char a and say, okay, using this little stuff, star and greater than, we can say, no, I want to parse this, but I want to ignore it if it's parsed, ignore it and return forward instead. So I may have made a mistake. Yes, excuse me, it's not, it's cache sign, which is stored in data.functor. Okay, so obviously we parsed a char a, so we get forward. But if there is no char a, he said, okay, unexpected B, expecting A. So we use this solution to write a parser. There is a choice function in the parser which allows us to write a list of parser, and it will pick the one which is matching. So now we can simply use I need to import the needed function, this one. We need to say that the char plus is increment, the char minus is decrement, the char greater than is forward, the char less than is backward. Okay, the char point is output, the char comma is input, input. Sorry about this crappy French accent. And we'll forget about loop for now, just to test that. Okay, it was simple, yes. Parse test. We'll try to parse test using parse instruction, and a plus. Oh, it's increment. Minus, decrement, times. Oh, there is no times actually. It's greater than, less than, point, comma. Okay, now we want to parse many instructions. So parse instruction, it's a parser of a list of instructions. And it's simple as many parse instruction. And okay, it works. Very nice. Actually, I will just add something else, that if I'm writing crap at the end of the output, it will parse and stop at the first wrong character, which is actually a here, but it will parse something. I want to ensure that it parses everything, so I will force him to parse the end of file, which is actually p.erf. The little star and stuff here it's a different signification from the cache greater than. There is one first. There is the ordering. It means the thing which will be passed is on the left of the right, or the right, by the way, each side. But in the case of cache greater than, the thing on the left will be passed, but the thing on the right will be returned. On the sign on the case of the star and less than, the thing on the left will be passed first, the thing on the right will be passed then, but only the thing on the left will be returned. There is a different. You can deorder the arrow show the thing which will be returned, and if it's a star, it means that both are parser, and if it's a cache sign, a dollar sign, it means that only the one on the, in this case, on the left is a parser, and the thing on the right is not a parser, and you have to wrap it in the parser, because those stuff are supposed to return parser. By the way, we can, and now that I have add this kind of this end of file, it complains because there is an unaccepted A. Okay, so I'm happy because now it passes everything except the loop. Okay, now we'll set the loop. The loop is the car open. Okay. Then we ignore the car and return something in the middle. But because what will return in the middle is a parser, we use the star greater than. We'll return many parse instruction till the end of loop, and we will wrap this inside a loop. And I just forgot to put a P here and a comma here, and there is a S. Okay, this is really awful and may stress a lot of people, but actually all those symbols are really common in Haskell, and it's part of the toolbox. It's as common as the pointer arrow, or the dot, or the I mean, in C you have some symbols such as star A for pointers. You have A arrow B from access to a structure behind a pointer. You have something like something with bracket here for arrow access. Those stuff are really common in C, and so you forgot about them. You say, okay, yeah, it's common in C, now I understand them. And it's the same for in Haskell for all the operator star something or dollar something with or without the left or right greater than or less than. They're really common, and they have a really simple meaning depending on the context actually. But so for the first time it is a bit surprising, but once you understand what they're doing, it's easy. And what they are doing, it's just mapping inside function. For example, if I'm writing apps 1, 2, 3, I will map the apps function on the different element of the list. Okay. If I'm writing like that, I will put the 1 on place of all items of the list. Okay. Actually, the opposite is not possible, so that's no meaning in this case. Okay. Also, I can use the thing with the star. If I have a list with apps and negate, I can use the star and a list 1, -2, -3, and it will give me a list of the apps function applied on 1, -2, -3, which gives 1, 2, 3, and the negate function applied on 1, -2, -3, which gives us -1, 2, 3. Okay, and I can also use a list of 1, 10, 20, and use with only one side, and in this case it will totally ignore what's on the left side, and in this case it will totally ignore what's on the right side and replace it by the content of the left side. So in the case of list, it apply a function inside or it replace. Okay, and when you have the $sign, it's apply a function or replace by a value. If you have the star sign, it apply a function or replace by a value which are themselves in function. So it works for function. Now replace the word function by parser. With the $sign, you can apply a function on a parser, and it is what we are doing here. I mean, I have here a parser which return many instructions, and I will apply the function loop on it to store the parser inside the loop. So it's now a parser of loop of many instructions. In the case of the greater than, it means that it will replace this function inside, replace this value inside what was parsed with this parser. This is the parser which contains a greater than, and we'll replace by the parser which contains a forward. This is a parser which contains a less than, and we'll replace it by the parser which contains a backward. Okay, and in the case of the star less than or star more than, it means that we will just this is the parser, we will ignore it and use this parser instead. But we will apply the parser but ignore the return value. Try it. It works. Okay, so now I will try to parse some instruction. So for example, this contains a loop, and we have actually a list which contains a loop. Does it works with broken loop to up? No, unaccepted, because here we ensure that the balancing of the loop is correct. Okay, so now we can simply parse hello world, parse test, parse instruction, hello world. We have parsed our program, and let prg program, okay, and we can run it, run prg, and we'll get, oh yes, actually okay, prg was okay, excuse me, parse test is just a test function, so it just displays on the command line the result of the parsing, but we'll need a real parsing. So run parse and run a string case p.parse of there is a casing with some error. We'll just ignore the oh, by the way, we'll do something else. Okay, we'll use mapping. Okay, run the p.parse hello world. And this takes a context which is an empty string mostly. Parse text, the parser, a context, and the string we need to parse. Okay, it's not able to show the memory. I'm surprised. Okay, yes, I'm surprised about that, but actually let's we'll do the parsing. Okay, let's res tip the res, it's an either. Okay, and now we'll map. Either means that it may store parse error or some instruction. If we look at it, we see that it's write, which means that it works, the list of instruction, and we'll simply apply run inside on the list of instruction, and crap. Yes, because it doesn't. Okay, so we'll do manually because I'm and parse. Okay. Case the p.parse instruction will pass the string to parse in parameter. Left will return nothing, just because. Oh, by the way, we don't really care about it. We'll put strln error. And in this case, we'll run the program. No, yes, no. Yes, we don't really care about it. We'll get a memory from the we'll print the memory. Okay. And actually, it apply hello, it writes hello world and shows us the current memory. So we wrote a Brainfuck interpreter and parser in Haskell. The interpreter was really straightforward because we had to write the list of instruction, the memory, which was the more painful stuff, but actually I don't see if you realize, but by writing the different type of the function, Haskell helps me to avoid mistakes by telling me that I missed the empty case and stuff like that. So it was actually I just had to write and follow the lead of my editor. So it's interesting. The run function was straightforward too. I did the case one by one and it works. And the parsing is really compact actually, but it's because this library is compact. But you need to know that library and to understand, and perhaps it's the more tricky part, just because you may not be aware of the behavior of that library, but actually it's really compact. And yes. So see you soon, see you later, and yes, have fun. Bye bye.